Okay, as you know, I discourage the mindless use of equations. And of course, you can use equations to understand the principles, but I don't see a lot of evidence yet that that's working very well. Solve an equation, treat it as a formula, you plug it in some more or less predictable manner, you get a result, and you never really think back to the principles from which the equation came. So I've discouraged the use of equations without the use of principles. But now we're trying to summarize things. So you still need to pull all that together so you'll have the conceptual understanding of where everything comes from and how everything fits together. So you'll be able to do well in the final, which is going to occur in about 3 weeks. So what I've got here are some various principles and laws and so forth. The idea of the linear storing force has this relationship. Newton's second law says that mass times acceleration equal to net force, and I write that as mx double prime equals F net, because x double prime is the second derivative of position. And if it wasn't position x, if you're in more than one dimension, we write that as mr double prime equals F net. Even in one dimension, regarding x as a variable, as a vector instead of position, this still works. R is your then position vector on 1, 2, 3 dimensions, whichever. Okay. Now, not sure why I wrote A equals constant. It's an assumption that we use for uniformly accelerated motion. Don't remember how that's related. It's probably related to what I was doing over here, so we'll come back to it. It's not, it's one possible premise. Okay, and actually, yeah, I get it, okay. Here is one instance of F net equal negative kx. Also, you have F net equals mass times a constant acceleration. That works when the acceleration is constant, which is the first kind of acceleration that's usually studied in a physics course. I have my reservations about whether that's a good idea, because that, I think, kind of encourages use of formulas, and people are still trying to use the equations of uniformly accelerated motion to analyze the motion of a pendulum. Can't seem to cure people of that. So anyhow, here are two instances of a net force, and I probably should have, it was clear from the context we were discussing it, but let's just be clear. This applies that F net is constant, provided the mass is constant. Okay, now, so we have two F nets, and we early started analyzing with both of these to try to cure the disease of using uniform acceleration, the assumption of uniform acceleration when analyzing simple harmonic motion. We'll see if we're successful. I'm cautiously optimistic. Okay, well, we have those, and these are in no particular order. Okay, we're fielding questions from the entire range of the course. I'm just writing these down in whatever order, because you got to know them in whatever order. You can order them yourself, but okay, well, there it is. Okay, net force then is the sum of conservative and non-conservative forces. Okay, now that's a little hard to separate them out in reality. but we think of it this way. Any net force has a conservative and a non-conservative part. Now, that doesn't mean that the conservative or the non-conservative part couldn't be zero, okay, but we think of it having a conservative and non-conservative part. A conservative force, a force is conservative if and only if it's path independent. And example being, first of all, a linear restoring force. You stretch out a rubber band and it exerts a force from here to here. You come back at the same position. If it's an ideal rubber band, you get the same force you did as you were moving up. Now there's a hysteresis involved, so that's not really true for a rubber band, but it's not too far off. Which again is why a rubber band can give you something very much like simple harmonic motion if you suspend a weight from it. For an ideal spring, that would be true. And for other forces, like the gravitational force, if I lift something up, then when it's right here, it experiences exactly the same force as it would when I lower it at this point. Okay, a satellite, well, let's not worry about that right now. A little more involved, although I think we're getting an understanding of that. Okay, well anyhow, so that's a path-independent force. It's conservative. It's like you get the work back that you do on an object because you get exactly the same forces in this direction as you get in this direction. So if you go from here to here and back, the work done on whatever it is you're moving by the force is equal and opposite. If you go this way, you get work. You come back this way, you get the opposite work. Okay, that's the idea of a conservative force. Change in potential energy has been defined in a phrase that I told you to know, okay, and nobody ever does. Equal and opposite to the work done by the conservative force, okay? Or by the sum of all conservative forces. And that's summarized right here. Equal and opposite to the work done on whatever you're moving by the conservative force. Okay, the work, and I use a delta W for work for reasons I explained. We think of work as being done over an interval. So it's work over an interval to emphasize the interval nature of work, the relationship between the interval and the work. It really doesn't absolutely need to be there, and almost nobody else would write a delta there. Okay, so that's your parallel force times your delta x. Where, of course, if you're moving in the x direction, each of these things would have a positive or negative sign. In general, it's the integral of your f vector with your delta x vector, and actually we generalize it by an f dot ds, and that would correspond to a line integral. We haven't talked about that. At least not how you set up and do a line integral. That's something we're not allowed to talk about for semester. Sometimes I violate that. Okay, so anyhow, you have the definition of momentum, mass times velocity. You need to know where that comes from. You also need to know where this comes from, at least at the level of plugging A equals F over M into one of the equations of uniformly accelerated motion that you derive by two integrations on A and imposition of initial conditions, okay? And people are pretty good with that right now. Okay, so anyhow, there's your definition of work. There's your definition of momentum, which comes from just plugging A equals F over M into a different equation, standard equation of uniformly accelerated motion. And of course, there are integral definitions of these things. Okay? Impulse is F delta T. That comes from the same substitution that P comes from. You get this on one side, you get this on the other side. And then the fact that impulse is equal to change in momentum. Angular impulse is torque times delta T. Just totally by analogy with this, but it has its own effects that we've talked about. Okay, here's Newton's law of universal gravitation in its vector form. F12 is the force exerted by mass 1 on mass 2. R12 is the vector from mass 1 toward mass 2. The magnitude of the force is big G times little m big M over R squared, directly proportional to each of the masses, so it's directly proportional to the product of the masses, and inversely proportional to the square of the distance. So it's an inverse square law. This is less specific than this. This is very specific because what we do is we put a negative sign in front of this, and over here we have the vector from 1 to 2 divided by its magnitude, which makes it a unit vector, a vector of magnitude 1, in the direction from first mass to the second mass. We put a negative on it. Now we've reversed the direction. This is a vector from the second mass toward the first mass. We multiply that by the magnitude, and right there is our vector force. Okay? With this magnitude. For an orbiting, for a circular orbit, about a big mass, big M, of a small mass, about a mass, big M, there's a formula for our velocity, but that formula comes from just setting this quantity equal to centripetal acceleration, because you need a centripetal acceleration to stay in a circle, and that's only going to come from gravity. So we set v squared over r, or mv squared over r, let's say, the centripetal force equal to the gravitational force, which gives us the centripetal acceleration that we need to stay in the circle. So for a circular orbit, right there is your constant velocity for the orbit. And escape velocity, which was derived in one of the problems I hope you did, is just this. Pretty easy to derive. You do have to use an integral. Okay, now I got the change of potential energy is the negative integral of the conservative force acting on an object times its displacement. That should be a ds. And it should be a dot product of two vectors. Okay, so we have that. But that's consistent with this and the integral definition of work in a way that should be clear to you. Circular model, simple harmonic motion, circular model, that's all I'm going to say. You need to know it. Spent plenty of time talking about it. Okay, so these are the principles. Okay, these aren't formulas that you necessarily use, but you know, some of them are put into formula, most of them, I guess, into formulas. These are the basic premises, various premises, laws, etc. Another one that I wrote over here, where I'm just kind of writing some of the consequences of these things, is that velocity is the derivative with respect to time, and the prime is implicitly with respect to time. Velocity is the derivative with respect to time of position, and acceleration is the derivative with respect to time of velocity. From this, with the assumption of constant acceleration, you get your equations of uniformly accelerated motion, which you've got to use carefully. Don't use it for simple harmonic motion. Don't use it for the motion of an object in a changing gravitational field, like a satellite that's moving away from Earth a significant distance, with a significant I can't think of a less clumsy way to word it, just because I'm not real good with words right now, but if the proportion of its distance from the planet changes significantly, so that the ratio of this distance to this distance is not very close to 1, then you have to take account of the fact that the gravitational force changes by the inverse square nature of the force. Okay. Okay. Anyhow, that comes from all of this in a way that's very obvious in terms of from the definitions. Okay. This comes from this. You're supposed to know why. Or you're supposed to at least be able to verify, to know, and then to verify that this is a solution. And of course, you verify it just by plugging it into this form. So that, well, mx double prime would be negative kx. Plug this in, do 2 derivatives, use the chain rule correctly, and it works out. So you at least believe this, and then this is related to the circular model. This is where the circular model for simple harmonic motion comes from. Review that if you don't know. Potential energy equals 1/2 kx squared. Okay, well that's a nice formula, but you got to apply it in the right place. If you're not applying it to a linear restoring force, you screwed up. Okay? If you try to apply this to potential energy of a satellite, well, there's no rubber band between the Earth and the satellite, and gravity doesn't behave like a rubber band. Rubber band force is not inverse square. The further you stretch it, the stronger the force gets. The further you get away from Earth, the weaker it gets. Okay, well, okay, that's the problem with formulas. People will pull out a formula that doesn't apply because of a failure to understand the principles and the connections. Okay, well, work done by a net force is change in kinetic energy. Okay, well that comes directly from this, and I didn't even write down the definition of kinetic energy, but if you know where actually, yeah, I was talking about it here. I never actually wrote it down. Okay. I could, I guess. I could write down, and I know I thought of it, I just chose not to, but I'll go ahead and do it now. Kinetic energy is 1/2 mv squared. Okay, that comes right out of substituting again A equals F over m into one of the equations of uniformly accelerated motion, or the more sophisticated integral derivation. Okay, not difficult, but you're not going to be responsible for that. So anyhow, okay, work done by a net force is equal to change in kinetic energy. That's the work energy theorem. Now, a different statement of it is that the work done by non-conservative force is a change in kinetic plus a change in potential energy. And that simply comes from the fact that you have your net force being split into conservative and non-conservative forces, and the work done by the net force is then the work done by the conservative force, which is equal and opposite to the potential energy, and the work done by the non-conservative force, which is this. And you put this together with this. And yeah, you just need to know how to do that. I could say it, but I'm going to let you think it. Okay, and then you have work done is tau net delta theta, and more precisely, it's the dot product of tau net vector with the delta theta vector, or the integral of tau net with respect to the theta dot, your angular displacement vector. Okay. You have the impulse momentum theorem, which says that this is equal to this. You have the angular impulse angular momentum theorem, which says this angular impulse is equal to the change in angular momentum. I don't know that I have the definition of angular momentum there, although we talked about it in the preceding video and in class, but I don't know what's coming up over here, so let's see. Yeah, I did. Okay, so first of all, we did mention moment of inertia is what you get when you add up all your MR squareds, or ultimately when you integrate, okay, the MR squared contributions. And anything I could write down for that integral right now anything general that I could write down for that. You wouldn't understand it. Because we haven't prepared you to understand that. Okay, angular momentum, that's L, is I omega. So there's your angular impulse, angular momentum theorem. You combine this with your angular impulse. And as I said, I tried to keep principles separate from this, but that should really be kind of together with this. Okay, kinetic energy is 1/2 I omega squared. You gotta know that that doesn't apply to a ball that I throw. Well, yeah, it could to a ball that I throw because it could spin, but to a particle that's being thrown. It's got to have something with a moment of inertia, and that's your rotational kinetic energy. We did mention, incidentally, the ball rolling down an incline. There's a change in its gravitational potential energy, and there's a change in the translational kinetic energy of that ball regarded as a particle, but the ball really isn't a particle. It's also rotating due to the static friction that holds the surfaces together, but allows the rolling motion. So you have an angular kinetic energy and translational kinetic energy, rotational kinetic energy, translational kinetic energy. And the ball rolling down an incline does lose just a little bit of energy to friction. So a little bit of energy is dissipated. Anyhow, there we have that. Here we have this, okay? I wrote it down over here, but here it is. So I'm going to say, well, I didn't really write it down over here. Okay, actually I'm just going to remove it. Excuse the interruption. Okay. Centripetal acceleration is v squared over r. You can derive that from the circular model. You can derive that from isosceles triangles and limits, various ways. That can be derived. You should be able to derive it at least one way, preferably two. You have the square root of g m over r, which I'd written down over there redundantly, and escape velocity. Gravitational potential energy is negative of big G, big M, little m over r, obtained just as an antiderivative of the gravitational force. You also have gravitational potential energies, mgh. Now, you're going to use this for satellites when they're significantly changing their distance from the planet, from whatever they're orbiting. And you don't want to use this there because this assumes that your gravitation is constant. Okay? That's another one that drives me nuts. People trying to do satellite motion using a potential energy formula that only applies near the surface of the Earth. Okay? Really hope I don't see that. Okay, what else have we got here? A couple other things. Yeah. Don't know if I keep both of these here. Okay, seems to be working. And let's see, I think I can see that from the camera. Yeah, it's okay. Okay. You also have kinetic energy, 1/2 big G, big M, little m over r. But you got to know the context, which means it's really helpful to know how it's derived. Okay, you've been through a series of problems that should make that clear. That's for a satellite in a circular orbit at distance r. Doesn't apply with elliptical orbits. It gets a little more complicated. You have conditions of equilibrium. Something in equilibrium has zero acceleration, which means it has zero net force, which means if you add up all the x forces, you get zero. If you add up all the y forces, you get zero. And if you're in 3 dimensions, you add up all the z forces, you get zero. Didn't write that one down because it's pretty implicit. Also, your net torque is zero. Otherwise, you're going to get an acceleration of particles that aren't on the axis. Okay, so sum of your torques is zero. We also have this one, which is the velocity relationships before and after an elastic collision. And we haven't done all that much with it, but we're going to need to in wrapping up what we've done in the course. Okay, so we got a couple of weeks to review. Got a couple of weeks to pull this together. This is pretty much it. There aren't many new topics, just little riffs on topics that we've been discussing, been experimenting with, and so forth. So there you have it. That's at least the first part of our review, and take that as maybe a basis for understanding what comes next.